Hi, my name is Stanley, and I will be presenting our ICRA 2024 paper on Squirrel-inspired tendon-driven passive gripper for Agile landing. In recent times, legged systems have seen remarkable progress in pushing the boundaries of mobile robot systems. This is enabled by the versatility of their legs to traverse complex terrains where there are gaps and discrete footholds. For example, Salto is an example of a lightweight, single-legged hopping robot capable of modulating jump trajectories and achieving stable landings on narrow targets. However, there is clearly still a gap when we look at the performance of the mechanisms used in jumping and landing legged robots compared to their biological counterparts in real animals. Work such as SNAG has sought to address this by exploring the range of bio-inspired graspers mimicking bird feet. But there are still gaps in advancing this technology, especially with higher impact landings with robust and adaptable grasps. In this study, we take inspiration from the remarkable agility of fox squirrels to leap and land on slender rods. In our field trials, we observed squirrels utilizing a highly adaptable, non-prehensile grasp, where their paws do not achieve a complete force closure around the landing target. The remarkable stability of this strategy is enabled in part by their foot morphology, where we see elongated digits, thick foot pads, and a lack of opposable thumbs. By leveraging squirrel-inspired principles in our design, we aim to devise an innovative mechanical solution for a robust, high-impact landing. We present our gripper design SQRT, short for Squirrel-Inspired Rapid Tenodesis. Each digit of our gripper is composed of 4 rigid links, joined by 3 spring-loaded joints. We achieve a passive under-actuated tenodesis grasp by routing a tendon beneath the digits and around a wrist pulley. As shown, a deflection of the wrist drives an overall grasp closure. When landing on rods, we see that this coupling between the wrist deflection and the digit curling is particularly advantageous and allows for successive passive grasping. Dynamic landing experiments are conducted by arranging 2 of the squirt digits in parallel to prevent out-of-plane instability. This lander assembly is additionally front-loaded with a large metal plate such that the effective center of mass lies on top of the landing rod. The passive lander is then dropped with varying drop height, h, and horizontal rod location, xr, as annotated on the left. Using high-speed video recording, we are able to analyze the stability of each drop, characterized as either stable or an unstable undershoot or overshoot. In total, we performed dynamic drop tests on 6 configurations, representing a variation of several key mechanical parameters. Specifically, we considered low and high contact friction, weak and stiff joint springs, and the addition of damping pads. For each configuration, the performance is characterized by the overall range of drop heights and rod locations that yielded stable landings, as shown by the shaded green regions in each of these plots. Notably, configuration A on the top left, with low friction and low stiffness, performed the worst, while configuration F on the bottom right, with high friction and high stiffness, and the inclusion of damping pads, had the greatest stability range. Let's now examine the trends embodied in these mechanical parameters in further detail. Examining contact friction, we see that adequate friction is necessary to sustain a stable grasp. Landing on smooth cardboard with a friction coefficient of 0.2, we see immediate slipping after touchdown and eventual failure. However, we see that increasing the friction to 2.2 by adding grip tape virtually eliminates slipping and allows for stable landing and grasping. We also consider adding damping in the form of soft foam pads adhered to the bottom of each digit. We observe that these pads allow for stability at higher drop heights with larger impact speeds. Specifically, the damping decreases the rebound of the digit following the initial impact, which allows for better stabilization and grasping on the landing rod. Lastly, we also examined the role of stiffness in the joint springs. Similar to damping, stiffer springs have a positive effect on the impact absorption capabilities, allowing for stability at higher impact speeds and higher drop heights. We established a baseline for grasp stability by considering a simple model of a grasp with two frictional point contacts. We see that the range of feasible static grasps gives an upper bound on stability. Comparing with data from dynamic drop tests, we see that all stable grasps that occur after the dynamic drop test are bounded by the range established from static feasibility from the model. We conclude by highlighting a particular advantage of the non-prehensile grasp found in both the Squirrel and the SQRT gripper. Since a non-prehensile grasp does not mechanically lock around an object, ungrasping and disengagement is remarkably simple and intuitive. This motivates the use of this design in highly agile maneuvers with rapidly changing footholds, such as locomotion through arboreal environments. I'd like to end by thanking my co-authors and collaborators on this project, spanning a large range of disciplines at UC Berkeley. Thank you.